The 20th century was the dawn of a new era. In 1903, 70 days after the New York Times wrote flying machines as impossible for another million years, the Wright brothers performed their first flight. It had taken thousands of years to go from the sea to the air, but it would take less than a human lifetime to reach the next milestone: space. This year marks the 50th anniversary of the Apollo 11 moon landing. There are barely 70 years between the Wright brothers flying for the first time and Neil Armstrong stepping on the moon. There are people who were born before the first airplane who would watch the space race come to its apogee on live television. How crazy is that? The space race began in earnest with the 1955 launch of the first satellite, Sputnik 1, by the Soviet Union. 3 years later, the Americans would send their own satellite, Explorer 1, and immediately put the newly formed NASA to work on Project Mercury. Project Mercury aimed to send the first man to space, and for that recruited the Mercury 7, the first American group of astronauts. History would have it that Soviet cosmonaut Yuri Gagarin would earn that honor in 1961. But not to be outdone, the Americans decided that they would shoot for the moon. Literally.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
The Apollo program was born. It developed in parallel with Project Gemini. Project Gemini was designed to support the Apollo program. Its mission? Develop the US's space travel techniques and technology in preparation for the moon missions. Sending humans to the moon took almost a decade of blood and sweat, coming up with new technology from scratch because nothing like this had been achieved before. The mission required the creation of a completely new type of vehicle, one propelled with a booster of a power never before seen. But they did it. The Apollo missions began in 1967 with Apollo 1. Well, they would have. Apollo 1 would have launched on February 21st, 1967. This mission would have served as a crude test of the Apollo Command and Service Module, or CSM. The crew took part in a pre-launch test during which an accident occurred. The cabin caught fire. Because of the pure oxygen atmosphere, the fire spread fast. The pressure differential between the cabin and the outside prevented the hatch from being opened in time, and the crew perished. The following investigation led to a heavy redesign of the CSM, which flew for the first time during the next mission, Apollo 4. Wait a minute, Apollo 4? Where did Apollo 2 and 3 go? Well, Apollo 1 wasn't originally called Apollo 1, that was just a nickname given to it by the crew. Its real name was AS-204. NASA renamed it Apollo 1 posthumously in honor of the lost crew. In keeping with that change, NASA nearly renamed the other missions in the AS-200 series as well, which would have given us Apollo 1A, Apollo 2, Apollo 3, and the tragic Apollo 1 proper. Although they didn't end up renaming the entire series of missions, they did follow that naming sequence for the following ones. Therefore, the next mission was Apollo 4. On July 16, 1969 at 9:32 a.m. Eastern Time, a Saturn V rocket took off from Launch Pad A at Kennedy Space Center, carrying on its board Mission Commander Neil Armstrong, LM pilot Edwin Bunds Aldrin, and CSM pilot Michael Collins, as well as the CSM Columbia and the LM Eagle. Apollo 11 had taken off. The Saturn V was a fiercely powerful machine. It was the most powerful rocket ever built at the time, and even today, it still is. It stood a full 110 meters tall and weighed 2,970 metric tons. Its thrust was of 34.5 million newtons. That's a force roughly equivalent to the cumulative weight of 575,000 African elephants. Or, to put it another way, 11,600 Saturn V rockets. You've probably heard this explanation of orbits before. Sending something into orbit is essentially like throwing a ball, except you throw it so hard that the Earth curves away from the ball at the same rate as the ball falls towards the Earth, such that the ball is perpetually falling. It's in orbit. In a sense, sending something into orbit is essentially like throwing it at the ground and missing. The minimum speed at which that ball needs to fly is called escape velocity. On Earth, that speed is roughly 11,200 meters per second, more than 32 times the speed of sound. Incidentally, all this means there exist images of the Saturn V producing a sonic boom, which is pretty cool. Such power required that most of the Saturn V's volume be dedicated to fuel storage. In fact, only the cone at the top of the third stage carried cargo. For this reason, the rocket broke up into 3 distinct stages. Once a stage ran out of fuel, it became dead weight. It had to be abandoned. Despite all of its power, no rocket is capable of escaping Earth whole. The first stage, S1C, developed by Boeing, was 42 meters tall and 10 meters in diameter. It was powered by 5 Rocketdyne F1 engines, the outer 4 of which were articulated for course corrections. The second stage, S2, was built by North American Aviation. 25 meters tall, it was powered by 5 Rocketdyne J2 engines, the outer engines also articulated for maneuvering. The final stage, S4B, was built by the Douglas Aircraft Company. 18 meters tall and 6.6 meters wide, it was powered by a single engine. Unlike with the previous 2 stages, this engine was designed to be reignited once for the trans-lunar injection maneuver. More on that later. Beneath the cowling at the top of the rocket was the Saturn V's only cargo, the Lunar Module, or LM. Right above it, at the very top of the rocket, was the Command and Service Module, or CSM. Together, the CSM and LM formed the Apollo spacecraft. The spire at the very top constituted the launch escape system. In case of an emergency during launch, it would activate and propel the crewed module away from the rocket. The launch wasn't merely a trial of power, it was also one of precision. You see, going to the moon isn't as easy as just pointing the spacecraft at the moon and starting the engines. This is the trans-lunar injection I mentioned earlier. With a single burn of the S4B engine, the spacecraft has to be carefully placed on a highly elliptical orbit around Earth in such a way that it will be carried right up to the moon and fall into orbit around it. Numerous course corrections were performed during the flight to keep the spacecraft on just the right orbit. Once trans-lunar injection completed, the CSM separated from the final stage. The CSM had to flip 180 degrees to dock itself to the lunar lander before ditching the final rocket stage and then flipping back another 180 degrees so that the Apollo spacecraft point in the correct direction, all the while remaining on its transit orbit. We generally think of the moon as being fairly close. After all, we can see it in the sky. But how close is it really? Say, if I take this tennis ball to be the Earth, then the moon would be about the size of a marble. How close should they be? Like this? No. Like this? Like this? Surely not a full arm's length. No. They should be a full wingspan apart. In fact, you may have heard this before, but it is possible to fit all the planets in the solar system between the Earth and the Moon. July 20th. After 3 days of travel, Armstrong and Aldrin exited the Columbia and boarded the Eagle, undocked, and began their descent. Touchdown would occur at 2017 UTC, about 1.5 minutes earlier than scheduled. So, you know, good for them. After 6 hours of rest and preparation, Neil Armstrong exited the Eagle and, on July 21st, at 2:56:15 UTC, became the first man in history to walk on the moon. We all know the story. Neil Armstrong climbed down the ladder, stepped on lunar soil, left the first footprint on the moon, and said his iconic one small step speech.
It's one small step for man, one giant leap for mankind.
And then what? What did they even do on the moon? Obviously, they planted the American flag, but they also spoke by telephone with President Richard Nixon.
I'm talking to you by telephone from the Oval Room at the White House. And this certainly has to be the most historic telephone call ever made from the White House.
You know, just to really stick it to the Soviets. But beyond the political goals of the space race, Apollo 11 was also a scientific mission. The astronauts collected some 22 kilograms of lunar soil, 50 rocks, and 2 core tubes of the moon's surface. They also left behind a seismograph to study the internal structure of the moon, and the Lunar Laser Ranging Experiment. This device, a small reflective plaque left on the lunar surface, is still used up to this day to study the distance between the Earth and the moon through laser measurements. Apollo 11 also left behind more symbolic relics. A plaque with a drawing of the Earth and the crew and the president's signatures fixed to the lunar lander. Commemorative medallions bearing the names of the Apollo 1 astronauts. And a small silicon disc containing micro-miniaturized goodwill messages from 73 countries. In total, Armstrong and Aldrin spent 21 hours on the moon. Upon their departure, the ascent module of the lander detached from its base and rejoined with the CSM in orbit. The crew joined together again aboard the Columbia and abandoned the ascent module in orbit of the moon. By July 24th, the spacecraft had reached Earth. The engine was jettisoned in orbit, and the command module landed in the Pacific Ocean, where the crew was recovered by helicopter. There would be 6 more Apollo missions after that. Each of them furthered our understanding of the moon in different ways. For example, now we understand how the moon formed. Before that, we could only speculate about it. In the early days of the solar system, a small protoplanet impacted the Earth. The protoplanet was completely annihilated and material from the Earth's mantle was expelled into orbit. Eventually, this material bundled up under its own gravity and formed into the moon we know today. We haven't gone back to the moon since 1972, though. At the time, it just didn't seem worth it anymore. Disregarding the countless probes we've sent to study every object in the solar system, we instead built a presence in low Earth orbit. We've sent satellites, but also the Skylab and Mir space stations, and then the ISS, which has been continuously occupied since its inception almost 19 years ago. But that doesn't mean we couldn't go all the way back to the moon in the near future, though. Most recently, NASA announced its plans for the Artemis Program, a spiritual successor to the Apollo program. NASA aims to land a crew on the moon by Artemis 3 in 2024. However, we need a ship to get us there. Enter the SLS. The Space Launch System. It will be the replacement to the Space Shuttle program. Comparable to the Saturn V in size and power, it will be used to launch the Orion spacecraft, NASA's next-generation crew module. If all goes according to plan, the SLS will launch Orion for the first time during Artemis 1 as early as next summer. However, this time around, the scope of the mission is much larger than just a simple moon landing. NASA hopes to establish a permanent presence on the moon through the Lunar Gateway. The gateway would be similar to the ISS, a space station, but in orbit around the moon. It would serve not only as a command center for missions to the surface, but also as a transit for the inevitable missions to Mars during the 2030s, which will build upon Artemis's accomplishments.
But why space? What good does that serve the world to send people up there? Well, science, obviously.
Microgravity allows us to run experiments that wouldn't be possible on Earth. That's the reason we have the ISS. But we could also take advantage of Lagrange points. Every two-body system in space has them. Lagrange points are points where the gravitational pull from both bodies cancel out with the centrifugal force experienced by a spacecraft located at that point. Any satellite or station placed at one of these points will be fixed relative to the system. For example, Lagrange point 2 of the Moon-Earth system would give us a zone of complete radio silence, perfect for astronomical observations. But why send humans? Why not keep sending robots and probes? Robots have very limited autonomy. They are very good at doing one very specific task, and they require human supervisors for direction. That's problematic when accounting for the communication delay. Because the speed of light is finite, it can take anywhere between 3 and 22 minutes for a signal to travel from Earth to Mars. A human crew wouldn't have these limitations.
But beyond that, I want to answer with another question. Why go to space? Why sail the Atlantic Ocean? Why cross the Strait of Bering? Why climb down the tree? Because that's what humans do. We explore, we spread, and we discover. And we become better for it.
Humans are what they are because they dare do the insane. We only have this whole civilization, technology, culture because 2 million years ago, we dared to climb down the tree. Maybe Earth is just another tree we still need to climb off of. We climbed down one branch with Apollo. Artemis will be another. And Mars, yet another. And before we know it, we'll have left our tree and colonized our entire solar system.